네, 그러면은 이제 5일차 강의의 두 번째 이제 토픽, Dynamically Scheduled Pipelines, 다르게 말해서 이제 다이나믹 파이프라인 구조에 대해서 이야기를 해보도록 하겠습니다. 우리가 이제 그 전 시간까지는 이제 거의 이제 뭐 두 시간, 그러니까는 이제 거의 두 슬롯짜리 이제 토픽을 이제 통해 가지고 스태틱 파이프라인에 대해서 이제 배웠었죠. 그 스태틱 파이프라인은 사실은 그 초기에 그 컴퓨터 프로세서 아키텍처에 이제 적용되었고, 그리고 이제 심플한 하드웨어가 이제 가능하다, 그런 장점이 있었지만, 스태틱 파이프라인은 결국에는 컴파일러에 이전할 수밖에 없는, 데이터 디펜던시 때문에 해저드가 발생할 경우, 이런 동작들은 예측은 가능하지만은 그런 데이터 해저드를 어떻게 이겨낸다든지 이런 역할을 하기가 이제 어렵고요. 그 다음에 이제 그 컴파일러가 여러 가지 이제 옵티미제이션 테크닉을 우리가 이제 적용을 할 수는 있지만은 그 위에 그 다이나믹할리 이제 발생하는 캐시 미스나 아니면 여러 가지 이제 상황에 대해서 그 컴퓨터 하드웨어가 이제 다이나믹할리 그 대응하기가 어렵다라는 그런 단점이 있습니다. 그래서 이제 이런 그 파이프라이닝 스토어를 발생시키는 이벤트가 이제 발생할 경우, 어쨌든 캐시 미스나 이런 해저드 이런 케이스가 되겠죠. 그런 이벤트가 발생할 경우에는 그 스태틱 파이프라인은 하드웨어가 이제 대응을 할 수가 없고요. 그렇기 때문에 퍼포먼스가 그 디크리스 되는 그런 단점이 있습니다. 그래서 이제 그거를 해결하기 위해서 나온 구조가 그 Dynamically Scheduled Pipeline, 쉽게 말해서 Out of Order Processor라고 이제 우리가 말하는 그런 모던한 그런 프로세서 구조가 나왔습니다. 이 Out of Order Processor 구조는 지금 현재 거의 사용되고 있는 하이퍼포먼스, 거의 모든 하이퍼포먼스 프로세서에 적용이 되고 있는 그런 아키텍처라고 여러분들이 생각하면 되겠습니다. We learned about the static pipeline architecture, and then as I mentioned, the static pipeline architecture is a simple architecture which is applied for some old generation computer processors. And then also this static pipeline architecture has some advantages such as the simple hardware implementation, and then due to this simple hardware structure, we can apply the best clock frequency. But the static pipeline architecture cannot handle some dynamically clock wasting situations, such as the cache miss or some data hazard, the inevitable data hazard. So we can apply some compiler techniques to optimize the performance of static pipeline architecture, but there is still we have the limitation of performance limitation, and then particularly if cache miss occurs, the performance of the static pipeline processor is significantly decreased. So in order to overcome this limitation, the researchers invented the dynamically scheduled pipeline architecture, and then we call this architecture as the out of order processor. And then the feature of this dynamically scheduled pipeline is that the hardware controls the execution of the instruction dynamically. So, for example, if the cache miss occurs, then hardware selectively execute some irrelevant instructions. with the regardless of the order of the instructions. So that is why this process call is called out of order calls. So let's see why it doesn't work. Oh. So this is the outline of this topic, the dynamically scheduled processor. So firstly, we will learn about the Tomasulo algorithm. This is some basic algorithm which implement the dynamically scheduled architecture. And then we will learn about the dynamic branch prediction. So actually, when we learned about the statically scheduled pipeline architecture, and also we learned about the branch prediction. But this branch prediction is very simple, and then this is the static branch prediction. Also, the compilers can help the branch prediction algorithm, but the compilers generate just the hint bit. Hint bit is the some taken or not taken prediction. So compiler predict the taken or not taken of the branch instructions. But what is the dynamic branch prediction? So hardware dynamically predict the result of the branch instruction. It's a conditional branch instruction. So hardware monitors the history of the branch instruction and then predict the result of the branch instruction. This is called the dynamic branch prediction. And then speculative execution. So this is very important topic in this courses. In this course, what is the speculative execution? Is the some actually we don't know about the result of the branch instruction. So until the branch is reserved, so we cannot actually the computer processor cannot execute the instructions after branch instruction. But if the execution of the instruction is stalled by the branch instruction, then the performance degrade is so significant. So the computer processor speculatively execute the instruction at the branch instruction. This is the speculative execution. So by applying this speculative execution, the computer processor performance is also improved, but the architecture and then structure of the computer processor hardware gets more complex. Then register renaming, and then speculative scheduling. This is also some important techniques to improve the performance of a computer processor. But also this can be some source of the security attack in the modern processors. That's true, but it's very important. And then the modern processor relies on these techniques to improve the performance. And then multiple instructions per clock is the parallel architecture, and then some vector or SIMD architecture, and the value prediction is to predict the value of some operand. So this is some topics which will be covered by this dynamically scheduled process architecture section. Okay, let's see the dynamic instruction scheduling. Okay, so we learned about the static pipeline, and then this, as I mentioned, this static pipeline only exploit the parallelism exposed to it. So that means that actually this static pipeline architecture is very simple, and then we know when the execution is issued and when the execution is committed. So committed means that the instruction complete its execution in the pipeline architecture, pipeline process of pipelines. So actually, so we know that the how many instructions exist in this statically scheduled pipeline architecture. So, and then ideally, the the number of running instruction is equal to the number of pipelining stages. And so these static pipelines only exploit the parallelism exposed to its stages, then the pipeline architecture. And then this compiler also know compilers also know these structures, and then the number of stages, and then uh, 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 some clock cycles for execution, and then data dependence between instructions. And compiler also knows that is knowledge, and then compilers can apply some optimization techniques to improve the performance in the static pipeline architecture. But as I also mentioned, this statically scheduled pipeline architecture cannot handle some dynamic event such as the cache misses or uh, some data hazard, and then some dynamic events which can happen in the uh, processor, and when instructions are executed in the processors. So, and then the limitation of this static pipeline architecture is that, so the number of actually the depth of the parallelism is limited by the number of pipeline stages, and that's the limitation. But we know that when the program is compiled, then 100 to 1,000 or some 10,000, 100 to 1,000 instructions can be generated. Actually, the size of the program is very large, and then we already know that. So that means that actually the potential of the instruction level parallelism is very large, because the size of program is very large. So that means that the control processors can expand the actually the size amount of instruction level parallelism. Actually, yeah, so that is the equivalent. Actually, that is proportional to the size of the programs. But actually, it is not practical to increase this instruction level parallelism, the amount of ILP to the size of the programs. But it is all. But we can imagine that so the computer processors can handle some hundreds of instructions at the same clock, or at the same clock cycles. So that means that, so as the program size is very large, then we can increase this amount of instruction level parallelism. But with this statically scheduled pipeline architecture, this ILP level is limited by the number of pipelining stages. So we can increase, but so how can we increase this amount of instruction level parallelism? So it's not easy to apply some compiler techniques. So if the hardware can dynamically handle some event such as the cache misses, or some data hazard, or some other event that waste some clock cycles, then computer hardware can dynamically handle this and the computer hardware can exploit the larger amount of instruction level parallelism. And then in order to exploit this larger instruction level parallelism, the computer processor need to execute the more basic blocks. So that means that the computer processor must cross basic block boundaries. So I will explain about the basic block later. But actually the size of the basic block is normally 4 or 5 instructions. It's very small. The size of basic block is very small. So, and then we already learned that the compiler's optimization techniques can be easily applied inside of the basic block, but also we can apply this compiler techniques across the basic block, such as the loop unrolling. But it's this type of optimization technique is very limited. So the also the so the critical issue of this dynamic instruction scheduling is to cross the basic block boundaries, so across tens of branches. And then, so what is the uh, some basic basic theory no, no, basic rule or basic theory of the dynamic instruction scheduling? And then, so actually the computer processor is, we know that computer processor fetch the instruction from the instruction memory, instruction fetch, and then instruction decoding, and then execution, and then memory, and then write back. This is the basic sorry. So I will adjust the. So these are some basic operation of the computer processor, and then actually this basic we learned about this basic operations and the statically scheduling pipelining lecture. So and then what is the some basic ideal, and then what is the ideal cases to learn this execute these instructions? So actually we know that these are some execution unit. So these execution units are required to execute the instructions. And then we learned about this execution as the instruction type, integer type, or branch instruction, and then memory type instruction, and then floating point type instructions. And then if the computer processor try to execute the various type of instructions, then that means that the computer processor equips this type of execution unit. So it's some processing unit. And then when an instruction can be executed by these processing units or some execution units. So when the instruction can be executed, when so instruction requires an instruction requires the operand. It's operand is the data required by the instructions. It's the same. So if operands are ready and then execution unit is also idle, then instructions can be executed. And then we know that the program is composed of a bunch of instructions, like here. And then we know that there is some data dependencies between instructions, but if that means that the data should be prepared by some formal instruction, and this data written by this formal instruction can be used by some following instructions. So that means and then if only focus on the some a single instruction, single individual instruction, so instructions can be executed when the operands are ready, and then execution unit is idle. So that's the some basic baseline idea of this dynamic instruction scheduling. So what's the basic idea of the dynamic instruction scheduling is that to separate the instruction decoding from scheduling execution. So that means that here is the execution unit, and then the instruction is decoded, and then instruction is allocated to the some ready actually idle execution units when the operand of instruction are ready. And that's the basic actually baseline idea, base ideas of the dynamic pipelines. So, and then if there are many instructions included in this instruction queue, and then we can select some ready instructions, as many as possible to the execution unit. This is the basic idea. And then the store of the disk store of the store is store of the some this instruction no, sorry, the store of this processor is only the caused by the structural hazard. So for example, the queue is full, store at the decode stage here, and then but the idea is not simple actually, but we only focus on the some readiness of a single instruction. So actually this dynamic pipeline architecture focus on the readiness of the single instruction, and then some readiness of the execution unit. So what is the challenges of this dynamic pipeline architecture? All data hazard. Actually, when we focus on the very simple five-stage in-order pipeline architecture, then we only focus on the low hazard, and then when the floating point execution units are included in the pipeline architecture, then we need to focus on the wow hazard, right after right hazard. But with this dynamic instruction scheduling, so actually the execution of the instruction, and then also the completion of the instruction is out of order. So instruction can be fetched in order, but the execution and then the completion is a commit. It's called the commit of the instruction is the out of order. So the all type of hazard can happen in the dynamic pipeline architecture. So it's the WAR. We need to also handle this all low hazard, wow hazard, and war hazard in the dynamic pipeline architecture. And then also how this is a very important issue to improve the performance of a computer processor. Then another challenge is to execute beyond conditional branch. So for this techniques, some modern processor applies the speculative execution. The speculative execution. Also this data hazard. Also, we need to handle this data hazard on register file and memory also, because the order of a memory instruction like load and store can be out of order in the execution. So we need to consider this data, all data hazard for the register file and the memory instructions. Also, this is some critical. So enforce the precise exception model. The precise exception model is very difficult to implement in the hardware, but it's also important issue in the processor design. Okay, let's start from the Tomasulo algorithm. So Tomasulo algorithm is some basic algorithm to implement the dynamic pipelines. So out of the processor. And then based on this Tomasulo algorithm, we will add some additional techniques like a branch prediction, a dynamic branch prediction, or speculative execution, the register renaming, and speculative scheduling. So Tomasulo algorithm is the basic algorithm to implement the dynamic pipeline architectures or out of order processor. So let's see the architecture of the Tomasulo algorithm, the structure of the Tomasulo algorithm. So when we learned about the some static pipeline architecture, the instruction is fetched from the instruction memory or instruction cache. So instructions are stored in the instruction cache or instruction memory, and then these instructions are fetched from this memory or cache. So there is the instruction fetch unit, and then this is called the ifetch. And then when the instruction is fetched, then this fetched instructions are included in the instruction fetch queue called the IFQ. So instruction fetch queue. So this is just some in order queue. So first in, first out. And then so instructions are decoded here and then dispatched by the dispatch unit. So it's called the dispatch. So instructions are decoded. So actually there are some different types of instructions like integer and branch, and then memory instructions like load or store, and then floating point instructions. So instructions are decoded, and then instructions are fetched to the different execution unit or different some issue queue, different type of issue queues for the different execution unit. So here, this is the issue queue for the integer and branch instruction, and this is the issue queue for the memory instruction, and this is the issue queue for the floating point instruction. And then there are some execution unit for the execution units, integer and branch, or address generation unit and floating point unit. Also, there are integer registers. There is integer register and then floating point register here. And then if the when an instruction is issued to the execution unit, the data can be fetched from these registers. So required data can be fetched from the registers or dispatched when the instruction dispatched, or the required operand data can be delivered from some result of the previous instructions via CDB is a common data bus. So what is the common data bus? This is common data bus is connected to here and here, and then connected to the register files. So when the execution unit complete its uh, execution or processing, then result is generated and the result is assigned to the common data bus. So this common data bus delivers the some result to the destination unit, which requires this result. And then there is the load store queue to handle the uh, hazard of the data memory, and then via this load store queue, the instructions can access the data cache or data memory. So these are the some basic structure of the Tomasulo algorithm, and then this Tomasulo algorithm can be separated into front end and back end. So the back end, the front end part can be mapped to the instruction fetch and the instruction decode stages of the static pipeline architecture, and the backend stage can be uh, mapped to the EX and MEM or write back stage of the pipeline stages. But this dynamic pipeline architecture separate this front end part and then this back end part. The front end part just fetch and decode instructions and then dispatch the instruction to the separate issue queues. And then in the back end part, the instructions are issued to the execution unit and then scheduled, and then the instructions are committed. So this is some basic structure of the dynamic pipeline architecture, and then you need to be familiar with this architecture. It's very important in this course. Okay, so actually I explained I already explained about this slide. And yeah, front end is the instruction. So it's the and somewhere else again. So in the front end part, instructions are fetched and then they are stored in the FIFO queue called the instruction fetch queue. So instruction fetch, and then this instruction is enqueued to the IF queue here, and then when the instruction is reached on the top of the IF queue is here, because the IF queue is just the FIFO queue. And then the instruction is decoded and dispatched to the HQ. There are three types of HQs: integer branch, memory, or floating point instruction. And then that is some unique feature of the dynamic pipeline architecture. So when instruction is here, then this instruction can be dispatched. It's called the dispatch. It's the same to the name of some Jirashi newspaper, paparazzi newspaper. So what is a dispatch? It's called the dispatch. So instruction is when the instruction is the top of the IFQ, this instruction is decoded, and this instruction is dispatched to the issue queue, one of the issue queues, if the issue queue has the available entries. And then this instruction can be dispatched even if the operands are not ready. So that means that if the operand is ready in the register file, then this data is read from this register file. But even if the data is not ready in the register file, instructions can be dispatched. And then, so that means that this requested data is are still being processed in the backend. Okay, so backend is actually I already explained about the backend also. And then and this slide summarizes the operation of the backend. So backend is composed of here is the front end, and this is the back end here, and then back end is composed of issue queue, execution unit, and then common data bus. So this issue queue is not FIFO. It's not FIFO. There is ready instruction. So ready instruction means that, for example, the instruction add R1, R2, R3. So this is an integer instruction, and then this is a destination. Then these are sources. So this instruction can be executed when this operand for this R2 and R3 are ready. So if the instruction is ready for the execution, then any instructions in this issue queue can be executed. So when these are ready, so first, if some ready data exists in rest file, and then the data is sent from the previous former instructions. So, for example, this add instruction can receive the R1 data from the R2 data from the previous former add instruction. So this when this instruction is complete its execution, the result data is allocated to the common data bus here, and then is delivered to this instruction issue queue, which is in the one of entries in issue queue. The incident branch instruction type. It's the data forwarding. It's very similar to the data forwarding. And then let's see how the data hazard are handled in the Tomasulo algorithm. In the Tomasulo algorithm structure. So actually, this Tomasulo algorithm used some tag information. So this tag information is actually the entry number of the issue queue, and this tag is assigned to the destination register of the instruction, and then this tag is equivalent to the entry number of the issue queue. And then let's see how the hazard are automatically handled by the Tomasulo algorithm and this tagging mechanism. So okay, so what's the tag? Let's start from the example of the add R1, R2, R3, and then this is the destination register of the add instruction. So let us assume that add is here. So add is decoded and dispatch it to the issue queue of the integer instruction type. So let us assume that there is an empty entry here. So this add instruction is dispatched to the is inserted to the entry number 2 of this is queue. So when this add instruction is dispatched to the integer issue queue, this is the entry number of the issue queue, then the destination register of this instruction is the R1 has the tagged with the entry number 2 of the integer HQ. So this is the R1 here. Let us assume the R1 is here, and then tag number 2 is attached to the rest file R1. So, and then let us assume that the following instruction, sub instruction, is also I4 and I5 sub instruction is also dispatched, and then we know that this R1 is the sub instruction has the data dependency with the add instruction, because the sub instruction requires the data from this former add instruction. So in this case, the add instruction is not executed yet, but sub instruction requires data. So in the Tomasulo algorithm, even though the data is not ready, this sub instruction can be also dispatched. So let us assume the sub instruction is sub here, and entry number 3 is allocated to the entry number 3. And then we know that, and then the sub instruction check the register file here, but in the R1 register file here, because the sub instruction need to read the data from the register R1. But this instruction can find that the R1 register file has the tag, and then this tag is valid. That means that the data is not ready. So data will be what data is being processed by the execution unit. So the sub instruction cannot read the data from this register file, but check this entry of the tag for the operand. So here, and then when the add instruction is executed, this add instruction is executed, then the result will be generated by this execution unit, and then result will be allocated to the common data bus. So this result is allocated with the tag number, and then the result value, it's a result value. So this CDB is delivered to the register file, and then issue queues. So all issue queues here, because the CDBs are connected to the register file and issue queues. So this is snooped to the all entries and then register file of this computer hardware. And then if the tag is the same, tag 2 is the same here, and then we know that the sub is the data from the tag 2, then data is returned to this operand of this sub instruction. Also, the data is delivered to this register file, because the R1 register file is attached with the tag number 2. As the tag number 2. So this the data is returned to the register file, also data is delivered to the serve instruction. If the data is ready for the serve instruction, then serve instruction can be executed. This is how the data hazard is handled by the Tomasulo algorithm, and this data hazard is the data hazard for the register file. Also, and then actually I skipped some previous slide because I want to show how the tags are managed by the Tomasulo algorithm in the Tomasulo algorithm structure. And then this slide summarizes this operation which I explained already. So this tagging mechanism is very similar to the register renaming, because the destination registers has some new names such as the tag number 2 in this case, in this example case. So it's very similar to the register renaming. So this is a form of dynamic register renaming. Register values are renamed to the execute. So tag number here actually is tag number. Okay. And then so another critical data hazard can happen on the memory. And then all types of data hazard, low and war and wow hazard can happen on the memory. And then this is also very critical issue. So when we write some program like a equal 1, b equal 2, c equal 3, and then a equal 1, 2, and a equal 3, then we also, for example, so when we write the program like this, a equal 1, a equal 2, a equal 3, then we assume that the order of this statement was actually this is the order of the memory instruction should be maintained or should be kept. So if the order is the changed, that means that the execution order is not in order, the execution order is out of order. What can happen? The final value of the a can be a equal 2, not 3. Why? The order can be changed. And then this is actually the very critical issue. And then so this order, so low, war, and the wow hazard, this order should be handled properly in the memory, and this is very critical issue. So in order to handle the data hazard on the memory, the Tomasulo algorithm, this structure has the load store queue. So load store queue is kind of a staging buffer to solve the memory hazard. So in order to actually in the Tomasulo algorithm, the store instructions are split into 2 sub instructions. This is because the load instruction only requires the one operand, because so this is the destination register, and then this is the some one operand. But store instruction actually requires the 2 operand. So R1 is the one of operand for the data, and then this R2 is the base address to calculate the address of this data. So for the store instruction, so actually for some efficient hardware implementation or efficient for efficient hardware, some this management so efficiently handles the data hazard on some hardware of the Tomasulo algorithm. The store instructions are split into two sub instructions. Like so, one instruction is to calculate the address of the store instruction. It is called the SDA, and then the second instruction to store the data is called the SDD. And then these two sub-instructions are included in the load store queue. And then this load store queue tracks the order of this load and store instruction, and then to solve this low, while, and wow hazard. So so what is important and what is the critical issue? Load and store. For example, uh, so what is so it's like a load instruction A and load store address A. But if this order of the load and store instruction uh, is upside down, then the final value for this address A can be different, maybe incorrect. So what is important? So let's see how the load store queues are exploited to manage the data hazard on memory. So this is some operation of the load and store instructions, and then this is the obvious. The loads can issue to address generation unit, and then load store queue. So when the load or store queues are load or store instructions are issued, then these instructions are issued to the address generation unit and load store queue when their address is ready. So when the actual load instruction is composed of load A and then destination register, and then for the memory operation, this address is important, and so address should be correct in the load store queue. And then store instruction is split into two instructions that calculate the address and then to store that stores the data to the register file. So why? So because the store instruction requires two operand for address and for data. And the goal is to uh, calculate the address as soon as possible, as early as possible actually, when the state operand for the address is ready. And the memory hazard, this is important and then these three types of memory hazards are reserved in the load store queue. This is some rule of handling the memory data hazard and memory hazard. But I already explained that load store queue keeps the tracks of order of load and store, and this is very important. So it keeps tracks of the order of the load and store instruction, and then when the instructions are dispatched, so these load store queue entries are reserved for the dispatched instruction. And when the load can access the memory, so just focus on just consider the load after write hazard. So what is the load after write hazard? So this read operation should be performed after the write operation when the destination of this write operation is the same to the actually destination. The operand of the read operation, actually this is the destination of the load instruction. It's the same. So what is the destination in the memory? It's the actually address. So actually load instruction is related to the low hazard. So how can you avoid the low hazard for the load instruction? It's the same. Write and read. Actually write is a store, read is the load, and then we check the address of the former store instruction. So load can issue to cache. The load can access cache if no store with the same address is before it. So in the load store queue, there is no former load store instruction which has the same address of the load. Then load can issue to the cache. The load can access the cache because the low hazard is reserved, and then for the store instruction need to consider the war hazard and the wow hazard. So actually you can also uh, apply the same techniques for the war hazard and wow hazard. So what is the war hazard? Read after war, write. So write. So people write the same address, the read should be performed. This is the war hazard. Then what's the war? So this order of the write operation should be maintained if the address is the same. This is the war hazard. So same technique is applied to the store instruction. Store can issue to cache if no store is the war hazard, and then load is the war hazard with the same address is before it. No store and no load instruction before the some store instruction. So this load store queue, these three types of data hazard can be reserved. And problem is that if an address is unknown, so address is not calculated yet, how can we handle this issue? So this unknown address is the same to the some star. 이거 그냥 모든 거죠, 모든 거. So it is assumed to be the same. So why? We don't know this address until the address is reserved. So actually this is the very conservative approach. So if the address is unknown, then this in the hardware it is assumed that this address is the same to the all other addresses. And then also in the Tomasulo algorithm, there can be the structural hazard. So what is the structural hazard? The resource of the hardware is not enough to handle the instructions or some request. So what is the critical hardware actually? What is the critical hardware of the Tomasulo algorithm or Tomasulo structure? So some queues, so instruction fetch queues or issue queues, and then load store queues. So there are many queues in the Tomasulo algorithm, the Tomasulo structure. So if these queues are the limited hardware resources, and then if the some queue is full, the instruction cannot be. So if the instruction fetch queue is full, instruction cannot be fetched. If the issue queue is full, then instruction cannot be dispatched to the some target execution unit, And then also the memory instructions cannot be dispatched if the load store queues are full. Also, some critical hardware resources, the common data bus. So common data bus is already occupied by some execution units. Then this common data bus cannot be allocated, or the function units also is the same. This is the structural hazard of the Tomasulo algorithm. And then also some critical issue is the control hazard. Uh, Actually, the limitation of actually the performance ceiling, or some performance disadvantage of the Tomasulo algorithm is that the branch works as the barrier of the instruction fetch. So the branch is very critical for the performance of the computer hardware. So what's the problem of the branch? So we don't know which instruction should be fetched by the branch instruction, because branch is just the branch is so the branch is just branch. So we don't know which instruction can go this way or that way. So this is the problem of the branch instruction. So in the Tomasulo algorithm, dispatcher stalls when it reaches the branch instruction, because we don't know the result of the branch instruction. Or branches are dispatched to the integer execution unit, integer issue queue, and then the dispatcher stores and then stops dispatching the following instructions after branch instructions. And then if the branch is resolved by the uh, instruction unit, what is the result of the branch instruction? Taken or not taken, the CDB. So if the untaken, so the next instruction will be executed, and then this is some happy case. So the next instruction is already patched in the instruction patch queue, IFQ. So if that branch is untaken, the dispatch resume from the instruction patch queue. If the taken, the instruction should jump to the target address, target piece. So this IFQ should be flushed, and then new instruction is fetched from the instruction cache or instruction memory. And then we may apply some pre-patch or some pre-decode techniques to improve the performance of the branch instruction. And it's possible. Also, another control hazard is some hazard for the precise exceptions. And then these precise exceptions are not supported by Tomasulo algorithm, because the execution of the instruction is out of order. So and then the commit of the execution is also out of order with the Tomasulo algorithm. So precise exceptions cannot be supported. Okay. And then there's some discussion and example here. Okay, let's see the time here. Please read this discussion, because I already explained about the hazard handling hazard by the Tomasulo algorithm, and then just to read this slide, and then if you have any question, then post your question on the Blackboard or Piazza. And then in this example, you can find that this hazard, and then you can see how the hazards are handled by the Tomasulo algorithm. And then I will show the uh, example operation of the with I will show the operation of the Tomasulo algorithm with the example code. So this is the example code here, and then this is the loop operation. So this is the instructions inside of the loop, and this example is so you can uh, see the same example code in the previous lecture for the static pipeline architecture. So here, and then this is the some operate operation of the Tomasulo architecture hardware. The integer branch instruction is executed one cycle, and then floating point operation is pipeline, and then takes 5 cycles. And then, as I mentioned, the store instructions are split into 2 sub-instructions, store A and store D for the address calculation and data stores. And then address generation unit and cache, accessing cache if the heap. Then cache stage takes 1 cycle. Then some stages such as the issuance, instruction issue, dispatch, and then common data bus take 1 cycle respectively. So this is the assumption of the Tomasulo architecture hardware, Tomasulo algorithm hardware. And then this table, we will for the dynamic pipelining architecture, then we will exploit this type of table. So what is this table? This is the instruction number here. And you can see the instructions here. And then we know that until the branch instruction here, is the one loop, one iterative loop, and then other loop is here. Uh, mm, and then you can see some steps of the Tomasulo algorithm here in each column. So dispatch of the instruction, then issue to the some issue queue, and then this is the start cycle of the execution. And then this is the start cycle of the completion of the execution, and then this is the cache, and then common data bus. And this is some comment for the operation. So let's see these instructions here, and then you can see that from instruction number 1 to instruction number 9 is the some one iterative loop, and then from the instruction 10 is the next loop iteration. So in the Tomasulo hardware, the instruction can be dispatched in order, like in each cycle 1, 2, 3. So you need to remember that instruction can be dispatched even though the operands are not ready. So instruction can be dispatched at every cycle, but this dispatch is stored after branch instruction. So this after branch instruction is dispatched, the following instruction cannot be dispatched because this hardware does not know the result of the branch instruction. And then after 1 cycle, this instruction can be issued. So issued to the no this load instruction can be issued because the data, we assume that the data is ready in the register file because this is the first iteration. So when instruction can be issued, if the operands are ready, then this instruction can be issued to the execution unit. So here the R1 is ready in the register file. So this load instructions can be issued. So this load instruction, for the load instruction, address is calculated at the AGU, address generation unit, and then it will take 1 clock. So the address generation is complete at 3, and then access the cache. There is no formal store instruction, so cache can be accessed by this load instruction. And then we assume that if the cache data is hid in the cache, the cache access is hid, then after 1 clock the data is allocated to the CDB. So this is the first load instruction, and then the second load instruction is the same because the R2 is also ready. So its cycle number is 2, 3, then 4, 4, 5, 6. How about this add instruction? Add instruction has the data dependency with the this load instruction. Formal load instruction is here. So what's the problem? When the add instruction is dispatched, this operand of the add instruction is not ready. So when the instruction is ready, so this F0 is ready after the data is allocated to the CDB at cycle 5 and 6, and then at by cycle 6 the F2 is allocated to the CDB. So at 6 the data is allocated, then we need the 1 cycle for issuance. So every instruction is issued to the execution unit at clock cycle 7. And then it's just start at 8 and then end at 12. And there is no cache staging, so the result can be allocated to the CDB at 13 because we need to wait for F1. And then how about the store instruction? The store instruction is store instruction is split into address and data instruction. So when actually the address is the operand is ready in the register file for the address instructions to address. So the address is generated and stop. And then CDB is not accessed by the store instruction because the store instruction just store the data to the data memory. And then how about this F2? So for this store data instruction, the data should be prepared by the former add instruction. So you need to wait F2 when the F2 is ready. So if F2 is allocated to the CDB at clock 13, so the storage data instruction can be issued to the memory unit at clock cycle 14. And then execution here, and the cache is accessed. And then this add instruction just use the add and sub instruction just to use the integer execution unit, and then there is no dependency with this formal instruction. So when this dispatch 6 at 6, 7, 8, 8, and then so The result of this add instruction can be allocated to the CDB at clock cycle 9, 10, 11. So you can see that the completion of the execution is out of order. And so you can see that this out of order execution. How about this BNEG? So actually BN is the dependency with this from a sub I instruction. So the result of a sub I instruction is completed is completed at clock cycle 11. So it can be issued at 12, then 13, and then the 14. So it's accessed here. So what's the problem? Until this PNE is reserved, the load this, and then this is the taken branch. So you need to wait for I9 is reserved. So this load instruction is fetched at 14. And then the same process is repeated for the next iterative loop. So this example shows how the Tomasulo algorithm works for the example code. And then with this table, I believe you can easily understand the operation of the Tomasulo algorithm. So you need to remember that it's out of order. And then so the execution of the instruction is dynamically controlled whenever the operands are ready. 네, 그래서 이제 제가 그 토마슬로 알고리즘에 대해서 이제 설명을 했고요. 이제 그 토마슬로 알고리즘이 어떻게 다이내미컬리 하드웨어가 인스트럭션을 이제 관리를 엑스큐션 하는지에 대해서 이제 설명했습니다. 그래서 그 우리가 이후에 이제 스페큘레이티브 엑스큐션이라든지 좀 더 이제 인핸스드한 그런 프로세스 구조를 배울 텐데요. 그래서 여러분들이 그렇지만 이 토마슬로 스트록 하드웨어 알고리즘이 가장 베이직한 그런 아웃 오브 오더 프로세서 구조이기 때문에 이 부분을 잘 이해를 해줘야 됩니다. 예, 그러면 이번 토픽은 여기서 이제 마치고요. 다음 토픽에서 다시 만나도록 하겠습니다. 예, 수고하셨습니다.